All right, let's dive right into this explainer and look at the architectural blueprint for modernizing fraud detection. Look, the landscape of financial crime has fundamentally shifted, right? So the tools we use to monitor it need a massive upgrade. We're living in this era of instant payments where funds literally settle in seconds, and AI-driven attacks can spoof identities at just an unprecedented scale. So today, we're going to explore exactly how to build a state-of-the-art fraud monitoring dashboard for 2026. We'll be leveraging real-time stream processing, graph networks, and unified data layers to get the job done. 95%. Let that sink in for a second. That staggering number represents the volume of false positive alerts generated by legacy fraud monitoring systems today. I mean, that is just an enormous amount of noise, overwhelming analysts every single day. Industry data consistently shows us that because older systems rely on siloed, static rules, rules that just haven't evolved with modern attack factors, up to 95% of the alerts your risk teams spend hours investigating aren't even fraudulent. It's a massive, massive drain on both time and resources. And, as the consultancy Parker points out, this isn't even a fraud problem at its core. It's actually an engineering and architecture problem masquerading as one. Get this, organizations are currently spending roughly $5 just to investigate every $1 of actual fraud loss. Crazy, right? And why? Well, mostly because they rely on fragmented tools. Imagine an analyst actively trying to stop a bad actor, but they have to manually gather data across 4 completely different systems just to resolve a single alert. By the time they actually piece the puzzle together, the money's long gone. So here's our blueprint for today. We're going to break this down layer by layer. We'll start with 1, the manual triage trap. Then 2, the unified data layer. 3, real-time stream processing. 4, graph networks and AI. 5, building the dashboard. And finally 6, key fraud dashboard KPIs. All right, starting off with section 1, the manual triage trap. Let's look at why the old ways of doing things are fundamentally broken. We absolutely have to transition away from the old approach. The one where analysts are forced to spend up to 48 hours manually gathering data across isolated systems and batch-based processors. Think about that delay for a second. 2 whole days to catch a fraudulent transaction that settled in literally seconds? Instead, we have to move to a 2026 approach. This modern approach is a unified, event-driven architecture that correlates signals instantly. An alert from a payment gateway shouldn't be isolated from your device intelligence platform. They need to talk to each other in real time to actually spot the anomaly. Moving right along to section 2, the unified data layer. Establishing this foundational plumbing is completely non-negotiable if we want to process things in real time. Now, notice right in the center here how Apache Kafka acts as the backbone of this new event-driven architecture. You can see how it continuously routes events, stuff like payments, web and mobile app signals, user logins, from multiple, completely disparate sources into unified, actionable streams. So instead of data just sitting in stagnant databases waiting to be queried, Kafka ensures high throughput, fault-tolerant ingestion. It basically acts as the central nervous system that feeds the rest of your advanced fraud detection pipeline. Next up, section 3, real-time stream processing. Moving up the stack, this is where we actually start transforming that raw streaming data into immediate, actionable insight. To make sense of all those continuous streams, we use something called complex event processing, or CEP. By using tools like Apache Flink for CEP, we can detect advanced fraud behavior dynamically, exactly as it happens. We're not just looking at one isolated transaction anymore, we're looking at stateful anomalies. Think about it like this. If a credit card is swiped at a physical terminal in New York and then used online from an IP address in Eastern Europe just 3 seconds later, well, CEP flags that impossible travel instantly. It identifies these patterns across multiple data streams and time windows to stop fraud dead in its tracks. Take a close look at how the entity relationships work here. By joining streams using shared fields, like matching a user ID or device ID across completely different topics, this architecture becomes incredibly powerful at sniffing out cross-stream anomalies. In simulated tests, this exact pipeline flow achieved a 94.2% true positive rate with just 480 milliseconds of average processing latency. Let me just repeat that real quick. You are catching fraud accurately in under half a second. That is a real game changer. Of course, we know not every engineering team wants to manage their own Kafka and Flink clusters, right? So for teams wanting to embrace a serverless option, Google Cloud provides a highly scalable alternative. You can use BigQuery ML to train machine learning models using simple SQL, stream the incoming transaction data through Cloud Dataflow, and then automatically trigger a pub sub alert the very moment a transaction hits, say, a 70% fraud probability.
And because it's fully managed, it scales up automatically with your transaction volume during peak retail seasons without even breaking a sweat.
All right, let's jump into Section 4, Graph Networks and AI. This is where we build a robust defense against those coordinated, highly sophisticated attacks.
Look, fraudsters rarely act alone. They operate in highly organized rings. And traditional relational databases, they really struggle to see these complex connections quickly. But integrating a graph database like Neo4j can uncover complex money laundering patterns up to 1,000 times faster than a traditional relational database. It excels at matching recursive patterns. It basically traces the flow of fraudulent gains, finds hidden intermediaries, and effortlessly exposes mass account takeovers just by visualizing the web of shared assets, devices, and IP addresses.
Which brings us to Section 5, Building the Dashboard. Now that our data pipelines, stream processing, and graph intelligence are all perfectly orchestrated, it's finally time to construct the UI.
According to insights from Hyperbots, a modern dashboard has to be so much more than just a chronological list of alerts. It really needs to consolidate these core components to give risk teams a true single pane of glass. Remember that analyst from earlier, struggling across 4 different systems? This completely eliminates that. It brings together real-time alerts, visualization tools for tracking network centrality, integrated analytics for deep diving into anomalies, and strict access control and segregation of duties tracking. This ensures internal compliance is always met seamlessly.
And finally, Section 6, Key Fraud Dashboard KPIs. To make this tool truly actionable for your risk teams, executives absolutely must monitor the correct metrics. ACI Worldwide provides these crucial benchmarks, and they give you really concrete industry average targets to aim for when you're tweaking your acceptance models. So you want your accept rate to sit roughly between 73 and 79%. Challenges, like sending an SMS verification code, for example, should be between 13 to 20%. Outright denials should hover at 2 to 4%, and chargebacks, where the real financial damage and penalty fees actually happen, should be kept right around 0.9%. If your dashboard shows metrics straying far from these averages, you know immediately that it's time to adjust your detection logic. This timeline is really the ultimate payoff of a modern architecture. When you assemble this entire pipeline, starting from a 1 millisecond data ingestion in Kafka, flowing into a 480 millisecond ML processing in Flink, resulting in a 1-second dashboard alert, the outcome is just phenomenal. We see a massive drop in total investigation times, from a sluggish 48 hours down to under 8 hours. Analysts have all the enriched data, the graph visualizations, and the risk scores they need the exact moment they open the case.
So I'll leave you with this provocative question to consider. Is your fraud dashboard learning, or is it just creating more work? Ultimately, your 2026 build must include an automated feedback loop. When your analysts close a case, whether it was true fraud or a false positive, that outcome absolutely must automatically refine your detection models. It has to learn. If you implement this architecture, your fraud operations will finally scale with your business instead of just burying your team in manual triage. Thanks for joining this explainer, and we'll see you next time.